Hello, so this video is for dot point 7.6, predicting, describing, and explaining trends in the physical properties of homologous series. So let's just go back to the fractional distillation column first. So the fractional distillation column essentially separates mixtures of alkanes based on the sizes, and you can see that as the chain gets longer, the boiling temperature required is higher. So you start at, I don't even know what this is, and then around 100 degrees when you get C5 to C7, 250 degrees when you get petrol, and then 325, 375. These are the boiling temperatures of these alkanes. So there is another way to sort of visualize this trend, and is to plot the boiling temperature against the this doesn't look as big. Oh, actually, no, that's fair enough. The boiling temperature against the number of carbons. This is just the first 8 carbon atoms, and you can see there is an increase. It's not a linear relationship, and you do not have to explain why it's not a linear relationship, but you can see there is an increase in the boiling temperature as you have more carbon atoms. So as the chain length increases, the boiling temperature increases. The question is why, and that is what you need to be able to explain as a chemistry student, because I don't think we've done any chemistry so far in this lesson. So that's the lesson agenda. Now, in order to explain this, we need to look once again at what is a physical property and what affects a physical property, which we actually have talked about last term. It has been a month and people did not do well on that part of the SAC. Anyway, so a physical property of a substance is a property that can be measured without changing the composition of the substance. That's the definition of physical properties. You don't really need to remember that, but you just need to know some examples of physical properties. So things like boiling point, melting point. Boiling point is just another name for boiling temperature. Melting point, melting temperature, or the states of something. Is it a solid, liquid, or gas at room temperatures? These are things that you can measure or observe without changing the chemical composition of a substance. Okay, now variations in physical properties of a substance depends on the strength of the bonding in the substance. So let's talk about different types of bonding once again. I actually have gone through this slide last term with you, but I'm just going to do it again. So let's say we have 3 types of solids. So you have solid copper, sodium chloride, and ice, which is solid water. H2O. Can't really say solid water, that sounds weird. So solid copper, this is the macroscopic structure of solid copper, which is the metallic lattice. So you have the copper cations in a cloud of delocalized electrons. So it is a lattice. There is no clear distinction between molecules. So it's just one uniformed structure. And then similarly, when you look at sodium chloride, this is an ionic lattice. You have cations and anions, so chloride ions and sodium ions, in alternating positions in one giant lattice. So in metallic and ionic solids, the atoms are held together by intramolecular bonds. So you have metallic bonds here, and then you have ionic bond here. Now, in the case of ice, which is also a solid, can I even turn this on? No? Oh, yes. Okay. You actually have, and you can see a distinction of different molecules. So this is one H2O molecule, and then you can see from one H2O molecule to another H2O molecule. It does kind of look like a lattice though. However, there are 2 things present. So within each molecule, is this thing gonna stop moving? Within each molecule, you have, oh, that's not helpful. Within each molecule, there is covalent bond. So there is covalent that is holding the hydrogen and the oxygen together, but between one water molecule and the next, so if you look at this water molecule and the next, these 2 are held together by intermolecular forces. So just a reminder, in the case of solid and metals and ionic compounds, you only have intramolecular bonds, but any covalent substance is going to have both intramolecular bonds within the molecules and intermolecular forces between different molecules, which would explain the difference in physical properties. Again, this slide actually explained last term. So when you want to melt, say, sodium chloride, what you're actually doing is you're trying to break the really strong ionic bonds between the ions, and that is actually very hard to do. And this is why the melting temperature of sodium chloride is really, really high, which is around 800 degrees. However, I think I may have to draw this out because I don't think the animation actually shows it really well. This is the animation. But essentially when you have water or ice, what you actually breaking when you melt it is not the covalent bonds. You're not breaking this. This is strong covalent bond. But what you're breaking is just this, which is the hydrogen bond. See how the molecules stay intact? It's just that they are now further apart from each other. So you're not breaking the covalent bond between the oxygen and the the oxygen and the hydrogen at all. You're just breaking the hydrogen bonds between the molecules. So they just further apart. And this is a lot weaker and requires a lot less energy to break than intramolecular bonds like ionic bonds. So they now further apart, probably have really weak interactions now. And this is why the melting temperature of a solid H2O is 0 degree, which is significantly lower than the case of sodium chloride. Okay, so the bonding which affects the physical properties. So for metal and ionics, it's just a recap of what I just said. It's the intramolecular bonds because they don't have any intermolecular forces. But in the case of covalent molecules, because when you change the physical properties, you're just changing the distance between the molecules. It's really just the intermolecular forces that's going to determine any difference in physical properties. And just to remind you, there are three types of intermolecular forces: dispersion forces, dipole-dipole interactions, and hydrogen bonds. And you may have to go back and recap on this in order to do the questions for this lesson. All right. Anyway, hydrocarbons are fairly easy to analyze. They're always nonpolar. You only have CH bonds and CC bonds. So they both considered nonpolar bonds. So two nonpolar bonds make nonpolar molecules. So always nonpolar, which means that the only type of intermolecular force present within a hydrocarbon is dispersion forces. So that's really easy. So when it comes to dispersion forces, the only thing that would affect the strength of dispersion forces is the amount of electrons that you have. So I don't think I actually have it on this slide. So more atoms, if you have more atoms, or if it's heavier, even though we haven't talked about mass yet, means that you have more electrons. But if you have more electrons, there is a higher chance of an uneven distribution of the electrons. You can form your temporary dipole. So you have more atoms, more electrons, you're going to have stronger dispersion forces. Okay. So if we go back to this graph, you can explain this trend using the structure and also the intermolecular forces of the molecule. So this is one way to explain. If this is a 3-mark explanation question, you want to highlight that alkanes are nonpolar and they have dispersion forces between the molecules. As the chain length increases, the strength of dispersion forces would increase, which means that more energy is required to separate the molecules. Hence, there is an increase in the boiling temperature. So you could explain this trend, and you have to use intermolecular forces to explain this trend in boiling point. Okay. There are two more things regarding intermolecular forces and physical properties of organic compounds that I want to talk about. This one is the effect of branching and stacking. So it's when you have molecules that have the same number of carbon atoms, but the difference is how the carbon atoms are distributed. So let's say I have A, and A has 4 carbon. This is butane. Okay, life is too short to be drawing hydrogen atoms, but here I am. And then B, so C4H10, so 4 carbon atoms, 10 hydrogen atoms, and B is going to have the same amount of atoms, but the distribution is different. So B is actually methylpropane. So it looks like this. So the question is, would they have the same boiling temperature? They have the same amount of atoms, and because both molecules are nonpolar, you only have dispersion forces. However, they will not have the same boiling temperature, and this is what is called the effect of branching and stacking. So when you think about multiple um, chains of butane, so if I have another butane here, I should say that life is too short to be drawing hydrogen atoms, and I'm drawing another 10 hydrogen atoms. But essentially, because of the linear chain, the molecules of butane could actually stack closer to each other. So the gap between these will be closer, and they can form stronger dispersion forces, because one of the other things the other thing that can potentially affect dispersion forces is the distance between the atoms. If the atoms are closer to each other, there is a high chance that you can induce uneven distribution of electrons from one atom to the next. So this, because of the linear nature of the molecule, they can be closer. However, when you get to something that has a branch, this branch is going to be in the way, which make it harder for the molecule to stack closely to each other. I mean, you can if you turn this molecule around, but the chance of you being able to do that is going to be lower than in the case of butane. So if I have another methylpropane on here, that's wrong. Oh no, that's not wrong. So if I have one here, then the distance between the molecules will be larger. So if you have a larger distance, that's going to weaken the dispersion forces between the molecules. So even though these two molecules have the same number of atoms, at the same type of atoms, this one is going to have a higher boiling point because it's going to have stronger dispersion forces just because the molecules can be closer to each other. So stronger dispersion forces. And this one's going to have a high boiling point. Okay, so that's the effect of branching and stacking. Very, very important in year 12. Definitely will come back in year 12. So if you get it this year, that's good. One less thing to learn next year. This is just a summary of what I just said, essentially. There is one more thing, and I'm not going to go into way too much details today because we're going to look at it more next week, but it's the intermolecular forces of hybrid organic compounds, which I think I have shown you last term as well using this example. So when you have something like this, we normally don't say, oh, this thing is polar, this thing is non-polar, but we just look at it as having a polar group and then a non-polar group. So obviously this is a CH bond and the CC bonds, and these are non-polar covalent bonds. But then you have the bond between C and O, and this is definitely polar. So this is definitely, C is definitely negative, sorry, positive dipole, and O is a negative dipole. And then the OH bond is also polar. So you actually have a non-polar section, which is here, and then you have a polar section that is here, which means that this molecule is capable of forming multiple types of intermolecular forces depending on what it is interacting with. So if you have another this is ethanol, by the way, and I'm going to teach you how to name this thing next week. I think next week, maybe week 4. So let's say if I have another one of these, and then there's an O and there's a H here. So this is also negative dipole, this is also positive dipole. Then you're actually going to have hydrogen bonds between the O and the H, because it's definitely polar, and this is hydrogen covalently linked to oxygen. So you're going to have hydrogen bonds here. But you can also have dispersion forces between different carbon chains. So if I have another carbon chain, so let's say maybe this OH is going to form some hydrogen bonds with something else on this side, but you can have dispersion forces between the carbon chains still. You do have dispersion forces between O and H as well, but they normally quite insignificant compared to the hydrogen bonds that can be formed, so we don't talk about them. But you can have here dispersion forces. So when you look at the hybrid molecules, you need to be very careful and actually pay attention to everything, because you can have more than one type of intermolecular force. I think I may give you one more example. So let's say if we have this one, CCl. So this molecule. So CH is considered nonpolar, but we're going to consider the CCl to be polar because Cl is fairly electronegative. Then you can have, all right, let me see. If I have another CCl here, my drawing is, the shape is like all wrong, but anyway, you can have dipole-dipole interactions between the carbon and the chlorine. It's not hydrogen bond, there's no hydrogen atoms present. So we can have between this carbon. Now you cannot have dipole-dipole interaction between the hydrogen and the chlorine because the hydrogen is not the positive dipole. But so one positive dipole to a negative dipole. So this is dipole-dipole interaction. Okay, but this carbon can form dispersion forces as well, just like everything else. So that's it for this lesson. We're going to do a few questions as a worksheet later.